So hello guys, in this proof we're gonna see why Hilbert spaces and the dual of Hilbert spaces are isometrically isomorphic to each other. So as we saw in the previous series, in order to prove isometric isomorphism, I just need to show that there exists a function from my space h star to h, and this function in the case of Hilbert spaces is injective, surjective, isometry, and if it's a complex Hilbert space, then rather than being linear, this function is antilinear. And this is essentially what I mean by antilinear. So if you look here and compare this, so when I take the coefficients out, rather than alpha 1 coming out, it's alpha 1 bar, which I can take out from this equation. And that's why if it would have just been alpha 1 in the case of real Hilbert spaces, but since I am considering the general case of complex Hilbert spaces, then it's alpha 1 bar. So let's start it with the proof. So let xt be the unique Rees representation of t belonging to h star, as we saw in the previous video. So by Rees representation, I mean that t of x is equals to the inner product of xt. That's the beautiful thing about Hilbert spaces. I have got this additional structure to it, and where this xt also belongs to h. So it's what I saw in the previous video. I saw that let h be a Hilbert space, and for every t belonging to the dual space of h, which is h star, and this t is a linear functional. Okay, so there exists a unique element xt belonging to h such that t of x is nothing but the inner product of x with xt. And now, in order to prove that the dual space of h is isometrically isomorphic to h, all I need to do is make use of my Rees representation. So again, we have done this kind of stuff before too, so it would be a bit easier in this video to understand. So if I have my mapping psi from h star to h given by psi of t is equals to xt, this is bijective. Its injectivity follows from the Rees representation. You see, why does the injectivity follows from Rees representation theorem? Because you saw that there exists a unique element. You see, so essentially that xt is unique, and its surjectivity follows from the fact that each element x belong to capital H defines a functional tx belonging to h star by the formula this. So essentially these 2 points come from the previous theorem of Rees representation. It's easy to see why they are injective and surjective. It's easier to see why they're injective and surjective. So I have psi of t1 is equals to xt. Okay. I again have psi of t2 is equals to x t1 x t2. And now I have psi of alpha 1 t1 plus alpha 2 t2 is equals to x of alpha 1 t1 plus alpha 2 t2. Okay, so I have these 3 formulas defined, and now let's look at our equation step by step. So I start from here. Okay, I start from here. Let me make it. Okay, so this thing here, you see, is exactly that what I have written here. So this can be replaced with this, right? So I can write this thing here as, let's do it. So I can write it as the inner product of x with x alpha 1 t1 plus alpha 2 t2 Riesz representation says that t of x is equals to the inner product of x and xt. So I can write this equation here in terms of t of x. So I can write it as alpha 1 t1 plus alpha 2 t2 times x. As simple as that. Whatever is here, I took it here and times x. See, from here to here is also simple. Okay, now the next part. Now since I can, and the next part is I just multiply it inside and I can write it as alpha 1 t1x plus alpha 2 t2x. Now I change this thing here again to my Riesz representation, which is alpha 1 x xt1 plus alpha 2 x xt2. Now when I have to take this alpha 1 inside, I would take the complex conjugate of it inside, because according to the laws of inner product, as we have seen before, go to the video on inner product spaces and Hilbert spaces, and then you will see a property of inner product, that when I want to take this here, so if I just want to take it towards this side, I would just use alpha 1, but if I want to take it to this side, I would have to use alpha 1 bar. Go and check the videos on inner product spaces if you have a bit of if you have forgot the concept. So x times alpha 1 bar times x t1 plus alpha 2 times, so plus x alpha 2 bar x t2. But you see, now everything is okay, because my xt1 was psi t1, so I can replace it as x alpha 1 bar psi t1 plus x alpha 2 bar psi t2. And so we have proved that my psi is antilinear. Okay, so this is explained here in these steps. Now, what's the next thing I want to show? So with the help of this, I was able to show that this function psi here is antilinear, which is a very good thing to do. Now, the only thing that remains to be shown is that the norms are equivalent. And now furthermore, we see that norm of t is equals to the sup norm of tx, norm of x equals to 1, which is equals to the sup norm. Now mod of tx is nothing but the inner product of x and xt. That's the Riesz representation theorem. So this is rise again, and norm of x equals to 1, and this is equal to norm of xt. So I understand that out of all these steps, you might have a small doubt here, and let's look at this. So when we look at, let's look at this one. So I know from Cauchy-Schwarz inequality that if I have this inner product, the modulus of inner product of x and y, it is less than or equal to modulus of x modulus of y. So the same argument follows here, that the modulus of the inner product of x and xt has to be less than norm of x times norm of xt. But since norm of x is equals to 1, therefore this thing is less than equal to norm of xt. But so if I put, let's take my x star and define my x star as xt by norm of xt, and it has the property, this x star has property that norm of my x star is equals to 1. So therefore And let me write it here. And for this value of x star, if I substitute this value of x star here, then this inner product becomes x star comma xt inner product is equals to, if I do the inner product, it turns out to be 1 by norm of xt and norm of xt squared, which is exactly equals to norm of xt. Now let's trace the steps again. So I came to the conclusion from this step that the sup norm of this thing has to be less than norm of xt. But for this value of x star, it is exactly equals to xt. So I say that, so again I saw that the supremum of this is less than or equal to xt, but for a special x, the supremum is exactly equals to xt. So the supremum is xt. So consider this example. So the maximum marks scored by the students is less than or equal to 95 in the exam. But for some student who got 95, so the maximum is 95. So if the supremum is less than or equal to something, but for a certain element, the supremum is exactly equals to xt, so the supremum is xt. So now once I have this property, then I can prove that this psi t is equals to xt and the norm of psi t is equals to the norm of t, because norm of psi t is nothing but the norm of xt, and thus I have the property of isometry. So psi from h star to h is an isometry, and it follows that psi is an isometric isomorphism. This is just one step I would explain again, which is this. So what happened? I took norm of t, which was equals to the sup norm of this. I take norm of x equals to 1, and I can use Cauchy-Schwarz to write this. From this, using Cauchy-Schwarz, I can say it is less than or equal to this quantity. I substitute norm of x is equals to 1, so it is less than or equal to xt. But for a certain x, for a special x star, the sup is exactly equal to xt as shown in this calculation. So the supremum of this quantity is exactly equal to the norm of xt. Okay guys, so now we proved that every Hilbert space H is isometrically isomorphic to its dual space. See you in the next class.